we see that both cell 1 and cell 2 are sourcing, and at this point, at this critical junction where there is this vertical line, this point PV cell 2 contributes 0 power. All the power is contributed by PV cell 1. And if you take all these regions less than this vertical line point, PV cell 2 does not contribute, it is effectively bypassed by this ideal diode. So only PV cell 1 is sourcing. So the characteristics, the operating point characteristic will be such that it will not take this path, but it will take this path, because that is the path, IV current path of the PV cell 1. And as PV cell 2 is effectively out of picture, this is the path now it will take. So if you redraw this portion such that the operating point takes this path in this region, it will look something like this. So this portion, this dark thick line portion, is actually now the IV characteristic of the combined cell with an ideal diode put in place like this. The advantage in putting this ideal diode is that PV cell 2 is bypassed whenever there is a voltage inversion or the PV cell 2 tries to act like a sink. Under such condition, this diode will save this PV cell 2 and it will look as though PV cell 1 alone is in the circuit delivering load to R0. Now PV cell 1 will deliver the full power to R0 alone, and no dissipation occurs here. So that is the advantage of putting this diode. You will be improving the efficiency slightly, and the characteristic also kind of takes this shape as indicated. Now this is the portion where PV cell 2 contributes power, and the remaining portion PV cell 1 contributes the power, and together of course will be the power power of the combined cell. So here you see that the contribution is only from PV cell 1. IV characteristic of the combined cell with an ideal diode put in place like this. The The advantage in putting this ideal diode is that PV cell 2 is bypassed whenever there is a voltage inversion or the PV cell 2 tries to act like a sink. Under such conditions, this diode will save this PV cell 2 and it will look as though PV cell 1 alone is in the circuit delivering load to R0. Now PV cell 1 will deliver the full power to R0 alone, and no dissipation occurs here. So that is the advantage of putting this diode. You will be improving the efficiency slightly, and the characteristic also kind of takes this shape as indicated. Now this is the portion where PV cell 2 contributes power, and the remaining portion PV cell 1 contributes the power, and together of course will be the power power of the combined cell. So here you see that the contribution is only from PV cell 1. I would now like to revisit this point where I said that this diode should be ideal if it has to effectively bypass the PV cell 2 when it is acting like a sink. In practice, this diode that you would connect is not an ideal diode. It will not have a cut-in voltage of 0 or close to 0. In such a case, will this bypass this PV cell 2? Will the circuit work? So, let us consider for now that this is effectively going to bypass this cell. Under such condition, PV cell 2 is out of the system, it is bypassed. If you take typical voltages, you will see that the voltage across the source is of the order of 0.6 volts to 0.7 volts. This has to overcome the potential across the load, the VT, and also the potential across the bypass diode as shown like this. This itself is of the order of around 0.6 to 0.7 volts. So this drop 0.6 to 0.7 volts plus VT drop will exceed the sourcing capability of PV cell 1. So effectively this diode will not actually bypass if it is not ideal. So it will work only if you make a diode, the bypass diode, which is having a cut-in voltage of at least 1/10 that of the cut-in voltage of the PV cell. That would make this diode more costly than the PV cell itself. So it is not a workable solution. So the via media is that in between solution is you put the bypass across a cluster of PV cells. Let us say you have some 5 PV cells or 10 PV cells or 100 PV cells in series. So let us say you have PV cells in a module. You can put a bypass for a module, for a cluster of cells. In such a case, this will work. However, note that there will still be issues of negative power within the module, that is within the module, as long as the overall terminal voltage is still positive. So now if you consider, instead of 2 single PV cells, we put many PV cells in series and we call that one as a module. Likewise, here are many PV cells in series and we are calling that one as another module. So you have module 1 and module 2. Now these two PV modules are connected in series to an external load. Now these can be protected with a bypass diode, because the voltage of these PV cells in series of this PV module will be high. It will be of the order of 35 volts to 40 volts, and it will be much greater than the cut-in voltage of a single diode that you would put in here externally, and that will definitely work. So here I have drawn this bypass diode here, which is bypassing module 2 under conditions when the module 2 starts going negative. That is, the module 2 when it tries to behave like a sink, this bypass diode will effectively take module 2 out of the circuit. We don't know which of the modules are having shading. So therefore, you have to put this kind of a protection bypass diode to every module which is there in the circuit. So you should also put a protection diode across here for the module 1, 2. As you see here, the module 1 is also having a protection diode. Whichever of the module has shading and starts to or tries to go to the sink zone of operation, the bypass diode will come and protect them effectively, removing that portion of the module out of the circuit. However, you should know that within the module there are cells in series, there are no protection diodes. There could be combination of diodes partially having a positive voltage and partially having parts of them having negative voltage. As long as the overall voltage across the module is positive, this diode will not come into the picture. So the internal diodes, if some of them are acting as sinks, they will be dissipating, so we can't help that. At the module level, you can protect it in this fashion. These PV cells in series, these modules, can effectively be represented in symbolic form like this. These are modules M1, M2, Mx, and so on and so forth, and each of these modules have many PV cells connected in series. And these are the protective bypass diodes, and they are connected across in this fashion such that they protect the modules whenever the modules try to become sinks. If there is partial shading and any one of the modules try to have an inversion in the voltage, these bypass diodes will effectively remove those modules out of the circuit and try to save them from becoming hot, and also to improve the efficiency of the entire overall circuit. PV cells in series. Let us take the case of two identical PV cells in series. I have captured the circuit in a GSM schematic, and this is the schematic. This part here is one PV cell, and this is another PV cell. So I have named this one as PV cell 1. It is having the insulation source, the current source 1 amp. There is a diode D1 and shunt resistance and a series resistance. Likewise, for PV cell 2, there is an insulation current source IP2, 1 amp, same value, D2, and R shunt and R series come into the picture. So this cell is connected in series to this, and the terminals where the load is connected is across at this point, where we have connected a voltage source, which is a sine varying source, which is supposed to provide the x-axis sweep. I have named the node as NVT for the output terminal, NVT2 for the terminal which measures the terminal voltage for cell 2, the bottom cell. If you have to find the terminal voltage for the top cell, which is the PV cell 1, it is NVT minus NVT2. I have included here the SPICE include directive. The file is pv.sub. In that one, inside that one is a diode model, default diode model, which is supposed to handle these two diodes, D1 and D2. So now we are ready with the schematic. Let us generate the netlist and simulate using ngSpice. Let me go to the simulation project folder, which is PVSim. There are three files that you will see here. Series.sch, this is the schematic file that we just now saw. Series.car, this is the circuit file which contains analysis. pv.sub, which was referred in series.sch through the SPICE directive. This contains nothing but the diode model, default diode model. Series.car actually has the transient analysis statement and an include statement for including the netlist, series.net, which we have not yet generated. We will just do that now. There is a series of control statements. One is to set the background as white and to set the foreground as black. Then the run command. So that is put into the control statement. Now let us generate the netlist file and then go into ngSpice. For that, first open the terminal window, go to the project subfolder, so we have all the relevant files here. I have here the netlist generation command, gnetlist -g spice-sdb output to series.net from the input series.sch. So this will generate the netlist. You can come back here and see that the netlist is generated, and then now call ngSpice series.car. So we are in ngSpice. ngSpice has used the run command, which was there in the .control statement. You can check the display and see that these are the vectors available for you to plot. Now we can plot and see the results. What is it that you would like to plot? You could open the schematic file so that it becomes a bit more easy for you to understand the variables that you are plotting. Now let us say we would like to plot the current through this output source, that is I, and the node voltage across this, that is the terminal voltage. How does it look like? So let us plot current V0 through the V0 source versus NVT. So we get a plot out like this. So rather than seeing a single plot, we can see a group of plots which will give you a kind of a relative idea of the various things. So let me quit this. Let us plot the I versus V characteristic of the PV cell 1, PV cell 2 and the overall cell. Plot IV0 versus NVT would give you the I versus V characteristic of the overall resultant PV module. And then IV0 versus NVT2 would give you the IV characteristic of the PV cell 2, and IV0 versus NVT minus NVT2 would give you the IV characteristic of PV cell 1. Now plot that, you will get this. Maximize that, and you will see that you have this characteristic. You see this line, the blue line, actually this is having two lines. One is the orange and the other one is the blue. This is that is I versus V for the two cells, they are identical cells. And the red one is for the resultant cell, and that's what you are seeing here, which matches with our theory. Now let us plot the power versus voltage curve for the three items, which is power versus voltage for cell 1, power versus voltage for cell 2, and then for the combination. So let us say plot I V naught. The I current is same for all because they are connected in series, same for all the three components, into, I'll say, NVT for the overall cell versus NVT. And the next plot will be IV naught into NVT2 for the PV cell 2 versus NVT, the same x-axis. IV naught into NVT minus NVT2 would be the voltage across cell 1 versus NVT. So this will give you the power versus voltage curves for the three cells. You see them here. So you see that the blue one, power versus voltage for cell 1 and also cell 2, orange superimposed, and the red curve is the power versus voltage curve for the series combination. I have here the circuit of two modules connected in series. Now this is module 1. This module 1 contains 5 PV cells. And these 5 PV cells are identical, all having 1 amp insulation current sources. They are connected in series. And there is another module, module 2, and they are also connected in series. Not all are identical. You have 2 of them having 1 amp current source and 3 of them having 0.7 amp current source, indicating that these PV cells have partial sharing. Now this module 2 and this module 1 are connected in series to the external load. In this case, the external load is this voltage source, which is acting as a sweep. If you look at the simulation project folder, you have 3 familiar files. Series.sch is the schematic file which we just now saw. Series.cir is the circuit file which contains the analysis statements, and PV